Hello friends, so good morning, welcome you all to my YouTube channel, welcome to my online learning sessions. So we all know that we are in the middle of discussion of the chapter Determinants according to your NCERT syllabus, alright, so NCERT 12th Mathematics textbook. So we have finished matrices, we have finished many topics related to determinants, we have finished 4 exercises also, minus, cofactors, areas, everything we have discussed, right. So also we have discussed the theorem 1, that is A into adjoint A is equal to adjoint A into A is equal to I. That is we have already discussed in the previous session. That is first theorem, right? So now let us see some notes. There are some note, right? So which you can prove by yourself by taking any simple determinants, right? So the first one, they said square matrix A is said to be a singular matrix if determinant A is equal to 0, right? Non-singular matrix if determinant A is not equal to 0. So here no need to prove anything. They are saying that if the determinant of any matrix is equal to 0, then that particular matrix is called as singular matrix. If determinant is not equal to 0, then that particular matrix we call it as non-singular matrix, right? That was the first one. Second one, if A and B are non-singular matrices. So what are non-singular matrices? Whose determinants are not equal to 0. A and B are non-singular matrices, then A into B and B into A are also non-singular matrices. And what is one more thing? They should be of same order. If A and B are the matrices of same order and their determinant is not equal to 0, that is they are not singular matrices, right? Then the product A into B is one matrix. So that matrix will also be non-singular. That is determinant of that particular matrix AB is not equal to 0. Similarly, BA also will not be equal to 0 and order of AB and BA also will be same. That is what it is there. Okay, that is second one, right? You can check it. You take any matrices whose determinant, any two matrices of same order, right? Square matrices of same order. Then check if the determinant should not be equal to 0. The determinant is not equal to 0. Then you can consider those matrices and then calculate AB and BA. Then you will find that AB and BA, the determinant value of AB and BA is also not equal to 0. And AB and BA obviously they will be of the same order. Okay. Next, the determinant of product of matrices is equal to product of determinant of the matrices. Right? See, the determinant of product of matrices is equal to product of their individual elements or their respective determinants. For example, product of matrices, determinant of product of matrices. A is a matrix, B is a matrix. Determinant of their product is equal to determinant A into determinant B, where A and B are square matrices of same order. So you can take A and B, any two square matrices of same order, calculate A into B, you will get a square matrix, then calculate its determinant, right, that will form your LHS, then calculate determinant A, calculate determinant B, right, separately, and then take the product of determinant A into determinant B, that will form your RHS. So then you can see LHS what you have got from calculation will be equal to RHS what you are getting from calculation, right. So you can take by any other small things, right. And fourth one is for any square matrix A of order n, determinant of adjoint A is equal to determinant A to the power n minus 1. Right? Determinant of adjoint A is equal to determinant A to the power n minus 1. Right? So here you have to take a matrix, then calculate its adjoint, then you can check in that way. There is one more method also, alright, using the property, previous property. What is the previous property? A into adjoint A is equal to determinant A into I, right? A into adjoint A is equal to determinant A into I, right? So we know that adjoint A into A, adjoint A into A is equal to what? Determinant A into I. Determinant A into I. This can be written as what? Determinant A 0 0 0, determinant A 0 0 0, determinant A. Okay, so now equating this, right, adjoint A into A I can write as equal to determinant A 0 0 0, determinant A 0 0 0, determinant A, right. So this is how we can do it. Now I can take out determinant A outside, determinant this determinant of adjoint A. Okay, no problem, leave it as it is, right? So now if I apply determinant value, right? So if I apply determinant value for this, what will be determinant of adjoint A into A? So now what you do is you just pause, you just make a note of this, then we can proceed. So how we have to proceed is determinant of adjoint A into A. So this will come out, right? Determinant A can be taken out, determinant A can be taken out, determinant A can be taken out. So this can be written as determinant A whole cube into 1 0 0 0 1 0 0 0 1, right? This can be written as 1 0 0 0 0 1 and 1 0 0 0 1 0 and 0 0 1. So now pause the video and make a note of this. So friends, I hope you have taken on. See what was there here? Adjoint A into A. There is a small correction here. Adjoint A into A is determinant A into I. What is determinant A into I? This will be a matrix. Make this correction. This will be a matrix here, right? So this becomes a determinant when I take determinant on both sides, right? Then this becomes determinant. Then only it can come out determinant A, determinant B, determinant C from both the sides, right? So here I can write this one. So this can be written as, see what is adjoint A into A? Determinant of, here we have determinant of product of two matrices, product of their individual determinants. So I can write this adjoint A into A, determinant of adjoint A into A as, okay, so a determinant of adjoint A into determinant of A. So I can write determinant of adjoint A into determinant of A as equal to, see what is this? I, determinant A cube into I, right? Determinant A cube into I. So now determinant A is there, determinant A cube is there. So that will cancel. What will remain? Adjoint A, determinant of adjoint A will be equal to determinant A whole square into I, right? Determinant A whole square into I. Now you can see here, what was the order of matrix we have taken? 3 cross 3, right? When it is 3 cross 3, what is the power we got here? 2. So if it is 4 cross 4, then what happens? Here we will get 4, then it will cancel with this, then 3 remains. If it is 5 cross 5, you will get 4 here. If it is 6 cross 6, you will get 5 here. So if it is similarly n, then you will get n minus 1. That is what is given here. I hope this proof is more clear to you people. So now you copy this down and then we'll continue with some simple problems in the next exercise, right? Okay friends, so I hope you have taken down those things and you have understood those problems. So let's continue with the next part. So this is theorem 4. What is it saying is a square matrix is invertible if and only if it is a non-singular matrix. So what is the meaning of if and only if? The meaning of if and only if is, so if it is a square invertible matrix, see what they are saying, a square matrix is invertible if and only if that matrix A is a non-singular matrix. Meaning of if and only if is, it is invertible if it is non-singular, and it is non-singular if it is invertible. Both should be true. If it is invertible, then only it will be non-singular, or if it is non-singular, then only it will be invertible, right? So if one thing is not possible, the other thing is also not possible. That is the meaning of if and only if, right? So now let's assume, see what we have assumed here in the proof. Let A be the invertible matrix of order n. We are assuming that A is a invertible matrix. Then what we should prove? It is a non-singular matrix, right? We should prove that it is a non-singular matrix. Either you can assume A as a non-singular matrix and you can prove it as invertible, right? Or you can assume A as invertible and prove it as non-singular. Both are correct only. Okay. So if A is invertible matrix of order n, then what is the condition for invertible matrix? A into B should be equal to B into A should be equal to I. So if A is invertible matrix of order n, if we have considered A as invertible matrix, then definitely there exists one inverse. As A is invertible, definitely there exists a inverse, right? So inverse for matrix n, there exists a square matrix of order n such that A into B is equal to B into A is equal to I. There exists a matrix B, right, of order n such that A into B is equal to B into A is equal to I, where I is called as what? Identity matrix of order n. Okay, so let's see, let's take this one. Determinant of A into B is equal to what? It is given as I, sorry, not determinant. A into B is equal to I, right? So if I apply determinant, determinant of A into B will be equal to determinant of I, right? So what is determinant of A into B? That is determinant of A into determinant of B. And what is value of determinant I? That will be 1. The value of determinant I will be equal to 1. Now you see here, determinant A into determinant B is equal to 1, right? So this is LHS's product of two terms or two matrices. And what is the value in the RHS? It is 1, right? So when LHS is product of two values and we have some product here apart from 0, then we can say that determinant A is not equal to 0. What happens if determinant A is equal to 0? This product becomes 0. If any one of the thing, determinant A or determinant B, either of anything if it is 0, then the product will become 0. It will not be equal to 1. As the product is 1, then definitely I can say with 100% confidence that determinant A is not equal to 0. Right? So determinant A is not equal to 0. Right? So as determinant A is not equal to 0, therefore A is a non-singular matrix. Right? A is a non-singular matrix. So similarly you can take a non-singular matrix, right? If A is a non-singular matrix, what is the thing? We already know that A into adjoint A, those things we already know. We can take that one and you can prove that A is having inverse. You can prove that this condition is to be proved, right? If you are taking A as non-singular matrix, then you should prove that this condition holds good. Then only you can say that A is invertible. Is that clear? So I hope the things are very much clear. The concepts we have gone very slowly and deliberately. I tried to explain the things very slowly. We have seen the note. Actually that notes, whatever we have discussed, those are some of the notes may have been given as theorems in your book, for which they have not provided any proof. There is no need of proof also. Directly you can use some common examples, you can get the proof for that. You yourself can generate the proof for those things, out of which I have given proof for one thing. Remaining 3 you can take the proof for yourself by assuming some examples, right? So and this according to your book is, I think this for this the theorem was to be proved, so we have proved it. So you can refer different books, you will get different problems, right? So you can try over them any point anywhere. If you are not getting, so then you please get back to me. You comment your doubts in the comment box. I will get back to you so that we can discuss to each other and then we can solve our doubts. Okay, so till now whatever we have finished, you go through that. Any doubt is there, you can get back to me, right? So here we are going to finish our session. We'll end the session here and we'll continue our session in the next class. We'll continue the concept in the next session. So we'll see different problems there. Till then, keep trying. Take care. Goodbye.